Carl, thank you for the introduction, and it's a pleasure to be here to talk about some of the work my lab has begun doing at MIT. Our lab is located at the Koch Institute for Cancer Research. So a primary question that my lab is interested in is how does diet impact tissue regeneration and cancer? And in my lab, we're really interested in looking at two extremes. We're interested in looking at low-calorie diets as well as overeating and overnutrition, because we think each of these, by studying each of these types of diets, we can glean new insights into how different nutrients and different dietary compositions can regulate processes such as tissue regeneration. So today I'm going to share some work that we've done looking at calorie restriction, which is this really interesting phenomenon where one reduces their calorie intake by 20 to 40%, and this has many beneficial effects such as a reduction in cardiovascular disease, a reduction in diabetes, and in some cases in model organisms, an extension in mean lifespan. On the other side of the ledger, we're also interested in looking at conditions of overeating, shown here by Homer Simpson, where the obesity epidemic is increasing significantly in the Western world. And unfortunately, overeating and overnutrition has untoward effects on organismal health. So ultimately, we want to study diet because it has a huge impact on aging, regeneration, and diseases such as cancer. So the reason we're interested in calorie restriction is that it does correlate with an increase in lifespan in multiple organisms. So the response to calorie restriction is conserved from yeast all the way to mammals such as mice. And even in some primate studies, there appears to be a mild potential increase in extension of lifespan. But in these primates, one problem with caloric restriction is that it's really difficult to do. So for example, in monkey studies, when they reduce calorie intake by 30 to 40%, these monkeys become delirious. And probably part of the reason why we see less of an effect in monkeys is because they're not doing the 30 to 40% reduction in calorie intake. It's more on the order of 10 to 15%. And even in cancer patients where it's been shown that calorie restriction retards the growth of these tumors, patients are unable to adhere to a strict reduction in calorie intake. So in addition to many of the beneficial effects of calorie restriction, there are also some negative aspects. Patients report feeling cold, and they also report having a reduction in libido. So for some of you in the audience that might be interested, there's actually a society called the CR Society International, where there are cohorts of humans that are under a CR-like diet, where they reduce their calorie intake anywhere from 10 to 20%. And this website has a lot of interesting information on the types of diets these patients are on, and as well as how they're being followed over time. So the organ that we're most interested in studying in the lab is the mammalian small intestine, where in this intestine, we have these stem cells here shown in green. They reside at the bottom of these intestinal crypts. And these stem cells basically give rise to all of the different cell types of a given tissue. And importantly, these stem cells here shown in green receive important cues from their neighboring cells, here called the panicell niche. And these cues are really important for maintaining the function of these intestinal stem cells. The other reason why we're really interested in studying the intestine is because we can engineer these mini intestines in culture. So one is able to take these stem cells and these neighboring cells from different dietary conditions, co-culture them in vitro, and generate these mini intestines shown here, where the stem cells are highlighted in green, and the morphology of these mini intestines in culture are reminiscent of the morphology one observes in the human and mouse small intestine. So this is a really powerful platform for beginning to understand how different dietary constituents in this 3D system regulate stem cell biology. And not only can we do this for mice, we can now grow these mini intestines from humans, and not only from the intestine, but from other organs such as the liver and pancreas and prostate. So what do we find with caloric restriction? In caloric restriction, we find that we get an increased number of stem cells. These stem cells self-renew, generate more stem cells, and are able to repopulate the intestine much more better than the intestines from mice that are on a normal diet. Importantly, this phenomenon is really mediated by factors generated by their neighboring niche cells. And we've identified this molecule that seems to be elaborated by these niche cells under caloric restriction called cyclic ADPR. And why is this important? So as a gastrointestinal pathologist, a biopsy that we commonly observe in the clinic is shown here, where this is a biopsy from a patient that's suffering from a severe bacterial infection. And even when one gives these patients strong antibiotics, one needs to wait a long period of time for this intestinal mucosa to repair itself. So we asked the question, if one were to give enemas of this compound cyclic ADPR, can one expedite endogenous repair in the intestine by activating the stem cells? And in preliminary experiments in mice, when we chemically injure the intestine with a compound by optical endoscopy, one can appreciate that there's ulceration and hemorrhage. And in animals that receive the enema of the cyclic ADPR versus those that receive mock enema, the mucosa has now healed after 3 days of daily enemas, raising the possibility that cyclic ADPR, this compound elaborated under this low-calorie state by the support cells of the stem cell, might be a way that we can utilize this in the clinic to help patients that are afflicted with intestinal damage and atrophy. So now I'm going to switch gears a little bit and talk about obesity. So obesity is a diet modifiable cause of cancer. And it only ranks second to smoking, which is the leading cause of cancer, particularly lung cancer and potentially pancreatic cancer. But in the Western world, particularly in the United States, the incidence of smoking is starting to decrease, whereas obesity and the overweight condition is starting to increase. And it's estimated that by the year 2030, obesity will become the leading modifiable cause of cancer. So what effect does high-fat diet-induced obesity have on stem cell function? So we placed animals on a long-term high-fat diet in mice. So these mice were on a high-fat diet for around 12 to 18 months. And just as a reference, the average lifespan of a mouse is around 24 months. So these mice have been obese for about 75% of their life. And what do we find? So we find that these stem cells from the high-fat diet condition are much more functional. They give rise to many more of these mini-intestines than their control counterparts. And this is just quantitated here, where we see about a 2-fold increase. So we then wanted to ask, and I think this really exemplifies the power of this organoid assay, we wanted to ask, is it the dietary constituents of high-fat diet, or is it obesity itself that's mediating these effects? And one of the main constituents of the diet is lard, and a primary component of lard is the fatty acid constituent palmitic acid. So we asked a really simple question. If one were to take these organoids, in this case from mice, where the stem cells are indicated in green, and just culture them in the presence of palmitic acid, what effect does exogenous palmitic acid have on the biology of these stem cells? And we find that from this picture, one can appreciate that there's more green stem cells, and when quantitated, this represents about a 2 to 3-fold increase in stem cells. And not only do we have more stem cells, but these stem cells are more functional, just as they were from the mice that were on a high-fat diet. They're more functional in giving rise to these mini-intestines. So to summarize, we're really interested in understanding how these different diet and dietary constituents regulate stem cells and regeneration and cancer. And in obesity, we think the reason that obesity increases cancer incidence is that in the obese intestine, one has more stem cells that are more rapidly proliferating. It's known that these stem cells can often serve as substrates that accumulate genetic mutations that go on to give rise to cancer. So if you have a larger pool of stem cells that are more functional, and you're exposed to a mutation, then you have a higher likelihood of developing these malignant stem cells that go on to give rise to frank cancer. And just lastly, a prediction would be that mice on a high-fat diet, like human counterparts who are obese, should develop more intestinal tumors, and that's in fact the case. So a mouse on a high-fat diet is larger than its control-fed counterpart, and a large fraction of these mice actually develop these invasive intestinal tumors. And these tumors are very similar in morphology to what one observes in human patients. Thank you.
So I think we have time for a question or two. If there's any questions for Omer, for Professor Yilmaz. So we started you off on a very rough scientific diet early on. So I don't know if that was right, but please use the mic.
I think it may make sense. Is there a conflict there? In the first case, you say when you have less calorie intake, you create more stem cell. Second case, high-fat diet, create more stem cells?
Yes.
So which one is good, one is bad? What was that?
Yeah,
conflict?
it's actually, you pick up on some, I didn't, because of the time constraint, I couldn't talk about it. But we actually think you have the same conundrum in a low-calorie state. It's an intervention that increases the number of stem cells. And we now think that if you're in a calorically restricted state and you're exposed to a mutation, or you come off of the diet and eat a broiled steak that has mutagens, the fact that you have more stem cells also raises the possibility that you might initiate more tumors. But the difference between caloric restriction and high-fat diet is, in both cases, you might increase the incidence of cancer. But in the calorically restricted state, once you get a tumor, it actually stays really small. And we think that what happens is, in the calorically restricted state, these tumors stay really small, and often they stay below the detection threshold. Whereas in the high-fat diet state, you're in an overabundant nutritional state. So not only do you initiate more tumors, these tumors are growing much faster. And my lab is interested in understanding these mechanisms of why these different diets, how they influence cancer incidence and overall tumor progression. But the mechanism of the increase in stem cell activity is completely different between the low-calorie state and the high-fat diet. In the low-calorie state, we think the phenomenon is mediated by the neighboring cells, and in high-fat diet, we think the phenomenon is actually mediated by the stem cells themselves. So these different diets, although they increase stem cell numbers, they do so by completely different mechanisms.
Please.
Yeah, we think it's probably going to be a combination, but we think actually in the high-fat diet case, we think constituents of the diet are really important at mediating the phenotype. But we're now looking at different types of diets, such as a Western diet, which is more carbohydrate-driven rather than fatty acid-driven. So I think it'll be interesting to compare and contrast these different diets in terms of their impact on organismal physiology. But importantly, I think for this venue, I think the cool thing here is one can grow these mini organs in culture, and one can now test these. One can now test the direct effects of these different nutritional constituents, either alone or in combination, on stem cells and overall tissue regeneration ex vivo.